Valence bond theory explains how a covalent bond is actually formed. To understand it deeply, first we need to learn the main postulates of valence bond theory. The first and most important postulate says that a covalent bond is formed by the overlapping of atomic orbitals of two atoms. We must understand that orbitals refer to the space or region around the nucleus where the probability of finding an electron is maximum. In simple words, we can say that an orbital is a region where an electron is present around the nucleus. When orbitals overlap with each other, they actually share electrons and form a covalent bond, which we will explain in detail. Moving toward the second postulate, only those atomic orbitals will overlap which contain unpaired electrons. We can understand this with the example of hydrogen. It has only one electron, and its electronic configuration is 1s1. As we can see, in this case, the s orbital does not have two electrons in it, so it is called an unpaired electron. But keep in mind, only those electrons will overlap that contain opposite spins. Moving toward the third postulate, it explains that the extent of overlapping determines the strength of the bond. This means that the strength of overlapping is directly proportional to the strength of the bond. If overlapping is more, the bond will be stronger, and if the extent of overlapping is less, then the bond will definitely be weak. The fourth and most important postulate says that a covalent bond formed between two atoms will be directional. This means that the direction of overlapping orbitals will determine whether a sigma or pi bond will be formed. To make it clear, let's understand it deeply. Actually, atomic orbitals can overlap in two ways. One is by parallel or head-to-head overlap, and the second one is perpendicular or side-to-side overlap. To clarify, let's take the overlapping of px-px orbitals and py-py orbitals. As we know, p orbitals have a dumbbell shape, and one px orbital will overlap with another px orbital in a parallel way. So the bond formed will be a sigma bond since the orbitals are overlapping in a parallel manner. But if we take the overlapping of py orbitals, they will overlap side to side or perpendicularly, resulting in the formation of a pi bond. One important point to remember is that every time an s orbital overlaps with another s orbital, it will form a sigma bond. Similarly, whenever a px orbital overlaps with another px orbital, it will also form a sigma bond. Now we will take the example of a hydrogen molecule to understand these postulates. As we know, hydrogen has only one electron, and its valence electron is present in the 1s orbital and is actually an unpaired electron. Similarly, the second hydrogen atom will have the same configuration, and its electron is also present in the 1s orbital. So, in order to form a bond, these two orbitals will overlap with each other. As I mentioned above, whenever an s orbital overlaps with another s orbital, they will overlap in a parallel or head-to-head way. So this means that in this case, a sigma bond will be formed between two hydrogen atoms. One thing we need to remember is that between any two atoms, a sigma bond will always form first, and after the formation of a sigma bond, a pi bond will be formed later. Also, remember that these orbitals form a bond at that position where the forces of attraction dominate over the forces of repulsion. We can take one more example to understand the formation of a sigma bond. Let's take the example of an HF molecule. Here, we can see that one atom is hydrogen and the other atom is fluorine. Since we know the valence electron of hydrogen is present in the 1s orbital, we now need to find out the valence electron of fluorine. By looking at the electronic configuration of fluorine, we can see that its valence electron is present in p orbitals, and the unpaired electron is present in the 2pz orbital. So, according to the postulates of valence bond theory, the unpaired electrons of both atoms should overlap with each other. So we can say that in this case, the 1s orbital of hydrogen will overlap with the 2pz orbital of fluorine. Always remember that whenever an s orbital overlaps with any other orbital, whether it's a p orbital or another s orbital, it will always form a sigma bond. So we can say that s and p orbitals will overlap in a head-to-head or parallel way and will form a sigma bond. And as a result of this overlapping, the HF molecule will be formed. Now let's take one example for the formation of a pi bond, so we can also understand it. Let's take the example of a nitrogen molecule. As we know, nitrogen always forms a triple bond with another nitrogen in the case of an N2 molecule. Here, one bond is sigma, and two bonds are pi bonds. First, let's have a look at the electronic configuration of nitrogen. Its atomic number is 7, and valence electrons are present in the p orbital. As we can see, nitrogen has 3 unpaired electrons, which again confirms that nitrogen needs to form 3 bonds. Similarly, the second nitrogen atom will also have the same electronic configuration. In order to form a bond, first of all, the 2 px orbitals of one nitrogen atom will overlap with the 2 px orbitals of the second nitrogen atom. Since px orbitals always overlap in a parallel way, we can say that a sigma bond will be formed by the overlapping of px orbitals from each nitrogen atom. So one bond is formed out of a total of 3 bonds. After that, the 2p orbital of one nitrogen atom will overlap with the 2p orbital of the second nitrogen in a side-to-side or perpendicular way, resulting in the formation of a pi bond. Again, we need to remember that after the sigma bond is formed, each additional bond formed will be a pi bond, and orbitals will overlap in a side-to-side manner. Actually, up to this point, 2 bonds are formed between nitrogen atoms, where one is sigma and the second bond is a pi bond. For the third bond formation, the 2 pz orbitals of each nitrogen will overlap in a side-to-side or perpendicular way, resulting in the formation of the third bond. Now, we can see that all 3 bonds, which were required to be formed between nitrogen atoms, are now complete, with 1 sigma and 2 pi bonds present. After understanding how valence orbitals overlap to form a bond, we need to understand some main differences between sigma and pi bonds. First of all, we can define a sigma bond in this way: the type of bond that is formed by the head-to-head overlap of atomic orbitals, where the probability of finding the electrons is maximum along the line joining the nuclei. Similarly, a pi bond is formed by the side-to-side overlap of atomic orbitals, where the probability of finding electrons is maximum above and below the line joining the nuclei. Now, moving toward the second point, a sigma bond is stronger due to the direct overlap of orbitals, but a pi bond is weaker than a sigma bond because it is formed by side-to-side overlap, which is less effective than head-to-head overlap. Moving toward the third difference, remember that free rotation around a sigma bond is possible because electron density is maximum along the line joining the nuclei. However, free rotation around a pi bond cannot happen due to the above and below probability of finding electrons. Here, free rotation will only happen when pi bond breaking takes place. A sigma bond is present in every bond formation. However, a pi bond is present only in double and triple bonds. Now, we will discuss concept of hybridization in valence bond theory. Actually, hybridization is a concept in valence bond theory that helps explain the shapes of molecules. According to VBT, atomic orbitals combine to form bonds, but sometimes the observed shapes of molecules do not match the expected shapes based on pure atomic orbitals. Hybridization occurs when atomic orbitals of similar energy mix together. The number of hybrid orbitals formed is always equal to the number of atomic orbitals that mix. These hybrid orbitals then arrange themselves in a way that minimizes repulsion between electrons, leading to the actual shapes of molecules. There are 3 common types of hybridization, such as sp3, sp2, and sp hybridization. In case of methane carbon is sp3 hybridized, so here 2 s orbital and 3 2p orbitals will intermix. These orbitals mix to form 4 sp3 hybrid orbitals. The 4 sp3 orbitals arrange themselves in a tetrahedral shape with bond angles of 109.5 degrees. In this case, each hybrid orbital forms a sigma bond with a hydrogen atom. Now moving towards sp2 hybridization. In this case, 1s and 2p orbitals intermix to form 3 sp2 type if hybridized orbitals. We can understand it with example of ethene. In ethene, each carbon atom forms 3 sigma bonds, 2 with hydrogen and 1 with another carbon. 1 2s and 2 2p orbitals of carbon mix to form 3 sp2 hybrid orbitals. The remaining unhybridized p orbital forms a pi bond between the 2 carbon atoms. The sp2 hybrid orbitals arrange themselves in a trigonal planar shape with bond angles of 120 degrees. Now let's move towards sp hybridization. In this type of hybridization on s and 1p orbital intermix to form 2 sp hybridized orbitals. We will take example of ethene. In ethene, each carbon atom forms 2 sigma bonds, 1 with hydrogen and 1 with another carbon. 1 2s and 1 2ep orbital of carbon mix to form 2 sp hybrid orbitals. The remaining 2 unhybridized p orbitals form 2 pi bonds between the carbon atoms. The sp hybrid orbitals arrange themselves in a linear shape with bond angles of 180 degrees. Now let's discuss limitations of valence bond theory. It is useful for explaining how atoms form bonds, but it has some limitations. One major problem is that it does not explain delocalized bonding. For example, in benzene, the 6 carbon atoms form a ring with alternating single and double bonds. However, experiments show that all carbon-carbon bonds in benzene are actually equal in length, meaning the electrons are not fixed between 2 atoms, but are delocalized over the entire ring. VBT cannot properly describe this delocalization. Another limitation is that VBT does not explain magnetic and spectral properties of molecules accurately. It assumes that electrons are localized in specific bonds, which does not match experimental data for many compounds. Was this video helpful for you? Let us know in comments. And kindly don't forget to like the video and subscribe channel for more such educational videos. So now goodbye from my side, and we'll see you in next amazing video.